Let's continue this set of problems about properties of real numbers. We did the number 1, 2, and 3 yesterday, right? Yeah. Number four. Look at the answer choices A, B, C, D. Which one is an example of identity property? Which one is the example of identity property? Number 4, identity property. Question: how many identities do we have? 2 identities, right? Yeah. One is additive identity, the other is multiplicative identity. Anyone can tell me what's the additive identity? 0, exactly. 0 added to any numbers, any number, we will not change the value of the number, right? So 0 does not contribute in addition. 0 is the additive identity. What's the multiplicative identity? 1. 1 times any number is still equal to the number itself. 1 does not contribute in multiplication. So 1 is the multiplicative identity. Let's look at number 4. Look at A, B, C, D. Which one describes identity property? Let's see this one. 2x times 0 equals 0. We know 0 is additive identity, right? But the operation on the left is multiplication. Even the equation in itself is a true statement. But what do you think? Is this is not an example for identity property, right? Yeah. It's just the 0 multiply anything equals 0. What about B? 2x plus 0 equals 2x. What do you think? On the left, we have addition. Yeah, 0 plus 2x is still equal to 2x. Yeah, that one is, right? Yeah. So it means 0 as the additive identity does not contribute in addition. 0 plus any quantity is still equal to the quantity itself, right? Yeah, let's look at the C. C itself is a false statement. Do you see that? 2x times 0 equals 2x. That is a false statement because the 2x times 0 is supposed to equal 0. What about D? D is a true statement. 2x minus 2x equals 0. But this is more like a inverse property. Yeah, look at the D. 2x minus 2x equals 0. You can see the left-hand side as 2x plus negative 2x. In other words, 2x and negative 2x are opposites. Remember opposites? Opposites is also called additive inverse, right? 2x, negative 2x, additive inverse, they add up to additive identity 0. So part D is more like an inverse property. Part B is identity property. Does that make sense? Does that make any sense? So that is identity property. The last one, number 5, distributable property. Distributable property, let's see which one is an example of distributable property. A. What do you think about A? A, we see left-hand side have a parenthesis. Right-hand side also have a parenthesis, right? And we know we apply distributable property to remove parentheses. But in option A, left-hand side has a parenthesis, right-hand side still has a parenthesis. The parenthesis is not removed, right? So the distributable property is not applied. This actually shows us a commutable property. X plus y and y plus x are equal. What about B? Negative 5 times parentheses. Inside the parentheses, we have x plus y. On the right-hand side, we have a negative 5 times x plus negative 5 times y. What do you think? What do you think about B? Answer choice B. This one. Is B an example of distributive property? Yes or no? Yeah. Look at the B. What's the coefficient of the parentheses? 95, right? Yeah. We multiply -5 by each member inside the parentheses. 95 times x, 95 times y, right? So B as in boy, that's the answer. Yeah, that's an example for distributive property. Do you see that? And what happened to C? C is a true statement, but is not a distributive property. It simply put a negative sign inside a grouping symbol. It didn't really dismiss the group, didn't really distribute, remove the parentheses. Her D is a false statement. Do you see that? D, answer choice D is a false statement because the left hand side is a negative, right hand side is a positive. The equation itself is a false. So press again. Yeah. I want you to please work on those 5 problems because they are very important for the test. Let's see, I think we have one more topic to cover before we start a review for test 1. Yeah, the last section, 1.7. The last topic, simplifying expressions. Here we have 2 concepts. How do we define a term? Let's look at the definition. Yeah, I want you please write down the definition. A term is a number. The number means constant. A variable or a product or quotient of numbers and variables raised to powers. A term, so here please take notes. A term is a number, a variable, or a product or quotient of numbers and variables raised to powers. Looks very complicated, right? Another way to understand the definition of a term is a term is an expression in which there are only multiply or divide or exponentiation of numbers and variables. You do not see plus or minus. That's another way to understand term or to determine if an expression a term or not. Okay, let's read the definition. A term is a number. A single number is a term. A single number is a term. Or single variable, like here, variable x. A single variable is also a term. Or a product or quotient of numbers and variables raised to powers. Like this one. 9 times, 9 is a number, multiplied by variable x, multiplied by variable y to the power 2. Okay? So as I mentioned earlier, there's an easy way to determine if an expression is a term or not. If inside the expression there's no plus or minus or any other operation like a square rule or then the expression is a term. And if in the expression you only see multiplication, division, exponentiation, yeah, the expression is the multiplication, division, or exponentiation of numbers or variables, then the expression is a term. Do you see what I'm talking about here? I think let's see those expressions that we apply the definition to see which of them are term, which of them are not, okay? Let's see the first. -10 is a single constant. Tell me please, is a -10 a term? Look at the definition. Is a -10 a term? Look at the definition. A definition says a term could be a single number. or single variable, or numbers and variables connected by multiplication or division or exponentiation, right? So single number is a term, okay? A single number is a term. In other words, you see, in this expression, you don't see plus minus. Be careful, this is a negative sign, it's not a minus sign, okay? There's no operation in it. And what about this guy? X here. Is X a term? Yeah, look at the definition. A term could be a single variable, right? Yeah, very good. Look at this expression, 9 times x times y squared. You see numbers, you see two variables, right? And the connection between the numbers and variables are multiplication, multiplication, exponentiation, right? So by the definition, is this a term or not? Is this a term or not? Very good. This one, 9x squared times y. Is 9x squared times y a term as well? Yes, it is, right? What about this one? Negative 7x times y squared. It is a term, right? What about this one? 2 over p. Yeah, the variable p is in the denominator this time. Would that be okay? Yeah, that would be okay because look at the definition. A product or quotient, right? Yeah. So you see division, that's okay. Division could be in a term, just not addition or subtraction. That would not be okay. So x is a term, right? 3 is a term. 3 is a single number. What about this one? Negative 4xy squared is also a term, right? So basically, they are all terms. They are all terms. Yeah, let me write something which is not a term. For example, square root of x times y. This is not term. Hold on. Raised to powers. And this one is okay. This one is a rational exponent. I mean this one, x squared minus y. X squared minus y. Do you see a subtraction? So that is not a one term, that is two terms. And this expression has two terms. The first term is x squared, the second term is negative y. Yeah, so the easy way to identify terms is you don't see plus, you don't see addition or subtraction. Sometimes I define terms as parts in the expression, which is separated by plus or minus or equal sign. Okay, if we have an expression, it is a term. Then in the term, we have, for the term, there are two parts, numerical part and the variable part. Yeah, so now we're gonna see how do we identify the numerical part and the variable part for a given term. Let me repeat it. Numerical part and variable part for a given term. Numerical part is also called a coefficient. All right, yeah. So let's see negative 10 here. We follow the order here. Negative 10, what's the numerical part? Negative 10. What's the variable part? It doesn't have a variable part, right? Yeah, so just the numerical part. What about 9x times y squared? What's the numerical part? 9, right? 9 is also called a coefficient. Where is the variable part? Variable part is x times y squared. The whole part that I colored in purple, in pink actually. Next up, 9x squared y. What's coefficient? What's coefficient? 9. What's the variable part? X squared y. The whole part x squared y, right? Awesome. What's the coefficient? What's the variable part? Perfect. What's the coefficient? 2. Yeah. What's the variable part? It's 1 over p. Yeah, this time is 1 over p. Yeah, 1 over p, not just p, because p is in the denominator. So it's 1 over p, that's the variable part. What about this one, x? What's the coefficient? What's the number in front of x? 1. Yeah, the number associated with variable x. If we want to write something, write some number like a multiplied by x, the number is 1, right? Without changing the value. So again, x has a coefficient positive 1, right? Variable part is the x. What about 3? What's the coefficient? 3. Variable part? There's no variable part, right? Okay. Yeah. The last one, what's the coefficient? -4. Yeah, be careful. The sign is a part of the coefficient. What's the variable part? Perfect. Yeah. So what if I give you -y? What's the coefficient? Coefficient for -y. Coefficient of -y. What's the number in front of y? -1. Yeah. -y is -1 times y, right? Right? So the coefficient is -1. The variable part is y. Does that make sense? Does that make sense? Okay, so that's the definition for term. Term is very important. We see terms all the time. Okay, next up, we're gonna know how do we define like terms. Very important definition. 2 or more terms are like terms if the terms have exactly the same variable parts. Yeah, any terms whose variable parts are exactly the same, are identical, then those terms are like terms. It's definition, so we need to remember as the definition, okay? Yeah. And now let's look at those terms that we have just seen earlier. I want you guys to identify which of them are like terms, which of them are not. How about, let's start from -10. Can you find like terms for -10? Yeah, in order to be the like term for -10, they need to have the same variable part, right? What's the variable part for -10? There's no variable part, right? So it means that anything that without a variable part would be exactly like terms. 3 exactly. -10 and 3. In those terms, -10 and 3, they are like terms. Can we combine them? Yeah, -10 plus 3 is -7, right? Okay, perfect. Let's move to this one. 9 times xy squared. We have already identified the coefficient is 9 in blue. Variable part is xy squared in pink. Can you find like terms for this guy? Yeah, that one. Yeah, 4xy squared, right? Yeah, I also have a -4 colored in blue, xy squared colored in pink, right? Yeah, you see those two terms. They have different coefficients. That's totally okay. Yeah, coefficients don't have to be the same, but they have exactly the same variable part, exactly the same, right? Then they are like terms. Could we combine them? Let's see, we have 9 pink here, and we have -4 pink there. If we combine them, how many pinks we have? What if you imagine the pink is a pink apple? So you have 9 apples here, and you have 94 apples there. So if you put them together, how many apples do you have? You have 9 apples here, 94 apples here. You put them together, 5 apples. Yeah, I'll show you that in detail later, okay? Yeah, that's good. You guys see those two things are like terms. And what about this guy? What about this? -7xy squared. Why not? -7xy squared. For that term, the numerical part coefficient is -7. The variable part, yeah, where's my pink color? Never mind. Let me color this purple here. The variable part is xy squared, right? The same way as the other two. Do you see that? Yes or no? Sammy, do you see that? Yeah. So among those terms, those three, yeah, they are all like terms because their variable parts exactly the same. Coefficient different, that's totally okay. Coefficient don't have to be the same. The important thing is the variable part has to be the same. And what about this guy? What about this term? Coefficient is 9. Variable part is x squared y. Why not? Neither has x, neither has y, it has square. Not exactly the same, right? And the variable part is x to the power of 1, y to the power of 2. But this is x to the power of 2, y to the power of 1. The variable part is not exactly the same. Even they do look similar. It's kind of confusing because it's so similar, but they are not the same. Has to be exactly the same. The variable part has to be identical. Then it's like terms. Am I clear about that? Yeah, like terms. So this one, if we look at all the terms, that one is just by itself. No other term is like terms of it, right? So x is also by itself. 2 over p is also by itself. So am I clear about what is the like terms? Yeah? Yeah. So if, am I clear about that? Angela? Okay. So if we have like terms in an expression, we need to combine them here. Combining like terms is to combine their coefficients. Let me explain. Let's take the 3 like terms that we have just seen earlier. They are 9xy squared. We have -7xy squared. We have -4xy squared. Yeah. Suppose in an expression, we have 3 terms. By looking at those 3 terms, we notice they are all like terms, right? Then we are able to combine them. So let me explain what I mean earlier when I say apple. You can say this is an apple, right? Xy squared, the variable part, you can color it as a purple apple. This is also an apple. This is also an apple. So basically what happened here is you have 9 apples. Yeah, let me explain. 9xy squared. That actually is 1, 2, 3, 4, 5, 6, 7, 8, 9. Do you see what I'm talking about? 9xy squared means you have 9 of those. You have 9 apples over there. Do you see what I'm talking about? Yes or no? Angela, do you see that? Like a 9xy squared, right? 9 times xy squared means you have 9xy squared over there. You have 9 apples over there, right? You have 9 apples over there. And here, you have a -7, -7 apples. And then you have -4 apples. So what happened is you have 9 apples, right? And I take away 7. So how many do you have? 2. And then you have 2 now, but I need to take a 4. So you owe me 2. Do you owe me 2? So what's the answer? What's the result after we combine them? -2, yeah. Do we have a -2xy squared? Do you see that? Yeah. You have 9 apples in the beginning. I take away 7, you have 2xy squared, right? But I again take away 4. So you only have 2, I take away 4, so you owe me 2. So that is a -2xy squared, right? Does that make sense? Yeah. So from this example, try to understand, make sense of this rule. How do we combine like terms? Combining like terms is to combine their coefficients. So later, when we see like terms, simply just combine their coefficients. In this case, coefficients are 9, -7, -4. Combine them, we have -2. And then copy down bring down the verbal part, and that's it. Does that make sense? Does that make sense? Okay. Yeah, that is what the like term. How do we combine like terms? Let's look at examples. Let me see. We have two here. Number one, which is an example of a term with a numerical coefficient 16. So with coefficient 16, which term has a coefficient 16? Which term has a coefficient or numerical part 16? Which one? The first one, right? Yeah, the first one, oh, this is so much. The first one has a coefficient 16. And what about this one? Yeah, look carefully. What's the coefficient of that term? Square, yeah, 16 square. What is 16 square? 256. Yeah, coefficient of that term is 256. All right? Yeah, coefficient is not 16, it's 16 square. So we do not choose this one. Correct answer is 16, x to the power of 4, y to the power of 9, right? Does that make sense? Next one, number 2, which is an example of a pair of like terms. Yeah, so we need to determine which option give us like terms. Let's look at A. Are those two like terms? Do they have the same verbal part? No, they are not like terms, right? Yeah, if the two terms are not like terms, we cannot combine them, just by the way. Part B, are they like terms? Yes or no? Looks similar, right? But not the same. Because this is x squared y, this is xy squared, so no. What about C? 66W. Do they have the same verbal part? Of course not. This one is T. Verbal part is T. This one has a verbal part W. They are two totally different variables. Yeah, what they have in common is their coefficient the same. But coefficient doesn't matter when we determine like terms, right? Yeah, even they have the same coefficient, it doesn't make them like terms. Yeah. If they are like terms or not, it's not up to coefficient, it's up to the verbal part. Part D, 5RY, 6YR. Are they like terms? Do they have the same verbal part? But this one is RY, this one is YR. Same thing, right? Remember, commutative property. Commutative property. So R times Y and Y times R are the same. So part D, as in dot, that's the answer for like terms, okay? Does that make sense? Let's simplify this expression. Let me see how many problems do we have. Yeah, one more. Let's simplify this expression. How about I give you a couple of minutes? You work on this problem on your own first. Simplify. When you see the parentheses, would you just apply the distributive property to remove the parentheses first, right? Yeah. So firstly, apply the distributive property. So -3 times -2x, right? -3 times -2x. Yeah. Yeah, exactly. And then you combine like terms. So when you combine like terms, you have 3 terms right now, right? 1, 3. Which of them are like terms? Yeah, you combine them. What are you gonna say then? Oh, you combine them all. So these two, they are not like terms. Yeah. Yeah, exactly. You have a solution? You need help? Distributive property. Yeah, how do you distribute? How do you distribute? Yeah, you need to find the coefficient first. And then you're going to multiply the coefficient with each number in the parentheses. Yeah, distribute. What's the coefficient? Negative. You're going to multiply -3 with each number in the parentheses. Yeah. So you're gonna bring down hx. You don't change that part. Yeah. And then you're gonna use -3 times 4. What is -3 times 4? 33 times 4. -12, right? Yeah. -12. -12. -12. Yeah. And then you multiply -3 by -2x. What is -3 times -2x? -3 times -2x. Negative times negative is positive, right? 6x. Yeah, positive 6x. Yeah. That's correct. Very good. Perfect. Awesome. Very good. Perfect. Yeah. All right. How about let's look at the problem together. When we have a parenthesis, when we try to simplify expression, and then we have a parenthesis, we want to deal with the parenthesis first, right? We want to free everybody. Then we can see which one could we combine them. Yeah. So first thing we do is to combine the like terms. So I'm going to, oops, that was too much. Make it smaller. So firstly, I'm going to bring down 8x because I didn't change that part at all, right? And then when I distribute, I know I'm going to distribute the coefficient. The coefficient is -3. Okay, the coefficient, when we apply the distributive property, the coefficient of the parentheses, the coefficient of the parentheses is -3, right? So we're going to use -3 times 4 plus -3 times -2x. Do you see that? Everybody, do you see that? -3 times 4 plus -3 times -2x. That's a so-called distributive property. If I write the formula, A times B plus C equals A times B plus A times C, right? When you apply distributive property, you need to identify the coefficient first. The coefficient in this case is A in the formula. You're going to use the coefficient A to multiply each single term in the parentheses. So A times B plus A times C. Do you guys see that? Coefficient in our case is -3, right? So -3 times 4 plus -3 times -2x. Everybody, do you see that? And then I'm gonna simplify the next step. You see, I don't rush to finish all the steps in one. Do one step at a time. And I bring down 8x. And let's see what is negative 3 times 4. Yeah, what is negative 3 times negative 2x? Yeah, very good. Now, how many terms do we have in the expression? How many terms? How many terms? Terms can be seen as the parts separated by adding, addition, or subtraction. How many terms do you see? Yeah, 3 terms. Term 1 is 8x, right? Term 2 is single number, negative 12. Term 3 is 6x, right? Among the 3 terms, do you see any like terms? Among the 3 terms, do you see any like terms? Yes. You see 8x. You see 8x and 6x. They are like terms, right? How do we combine them? You have 8 apples, and then I give you 6 more apples. How many apples do you have? 14 apples, right? You have 8x. What is 8x? 1, 2, 3, 4, 5, 6, 7, 8. That's 8x. And then now you have 6 more x. 1, 2, 3, 4, 5, 6. And together, you combine them all together, you count the number, you have 14x, right? Does that make sense? Yeah. And you also have a negative 12. Negative 12 has no like terms, so it will be just by itself here. And then the answer is simplified because 14x is one term, negative 12 is a term, and they are not a like term, so that's the simplified form. Am I clear about this problem? I guess distributive property might be challenging, right? Again, when you apply distributive property to remove parentheses. When you see a parenthesis, you need to get rid of the parentheses. You need to consider distributive property. How do you apply distributive property? You need to identify the coefficient for the parentheses first. The coefficient for this parenthesis, not 3, instead is negative 3. So the sign, you have to include the sign as part of the coefficient. Once you identify the coefficient, you're going to use the coefficient to multiply each member in the group. Had 2 members in the parentheses, right? Term 1 is 4, term 2 is negative 2x. We use the coefficient to multiply each term inside the parentheses. And then you simplify. Does that make sense? Does that make sense? All right, I think that should be the last thing for this chapter. Last thing for the chapter. Let me double check. Prime number, GCF, LCN, fractions, decimals, real number, number system, and those things. Okay. All right, guys, are you ready for review? How many problems in the test 1? You're gonna have 30 multiple choice questions in test 1. They take notes. This is a review test. Okay. Number 1, what's the smallest whole number? Yeah. Whole numbers include 0, 1, 2, 3, and so on and so on. The smallest whole number is not 1, is 0. Okay? I'm actually telling you the first problem. What's the smallest whole number? Please do not choose other numbers. The smallest whole number is 0. Any questions? Number 2, what's the smallest prime number? Okay, please look at your note. Yeah, you only have 4 answer choices. You only have 4 answer choices. Look at your note, the very beginning, the first day, the note. look at your note. I had two sentences. Make you to write it down. The smallest prime number is 2. Yeah, 2 is also the only even prime number, right? Yeah, please don't tell me 1 or 0. The smallest prime number is 2. Okay? I'm gonna count after the test 1. I'm gonna count how many of you get the number 1 wrong, number 2 wrong, okay? The smallest whole number is 0. The smallest prime number is 2. Okay. Next up, number 3. What's the GCF of 4 and 20? Yeah, good job. Yeah, so the reason GCF of 4 and 20 is 4, look at here, everybody, is because it's the first special case number 1, right? 4 and 20. 4 is a factor of 20. 20 is a multiple of 4. That's the special case number 1. In special case number 1, the GCF is a small number, LCM is a bigger number. Do you guys remember that? Yeah. So 4 is the biggest factor of itself. 4 is a factor of 20. That makes 4 the biggest common factor of both. So it's 4, okay? Yeah. So number 3 is the first special case for GCF. Number 4, am I clear? Do you guys need me to repeat that, to do it again? Okay, number 4, what's the least common multiple of 5 and 15? Perfect. That's a special case number 1 as well, right? So number 3 and number 4, those are the special case number 1. 5 and 15. 5 is a factor of 15. 15 is a triple of 5, right? 15 is the smallest multiple of itself. 15 is a multiple of 5. That makes 15 the smallest common multiple of both. That makes 15 the smallest common multiple of both. Yeah, special case number 1. It's gonna be here to remind you, okay? The GCF is a smaller number, LCM is the bigger number. Number 5, what's GCF of 4 and 7? You're gonna choose one number. What's GCF of 4 and 7? You don't choose this. What's the answer? 1. There's a number 1. Yeah. They do not have any common prime factor, but they do have only one common factor. The only one common factor is 1. So the GCF, the greatest common factor, is also 1. We know 4 and 7 are mutually prime, right? Mutually prime is the second special case. Second special case. We covered the very beginning of this semester. Huh? Second special case. Special case number 2. The two numbers are mutually prime. If the two numbers are mutually prime, GCF is 1, LCM is their product. How many times we talk about this? Yeah, I swear we make it very clear. Do you guys study the notes after class? You have to study the notes after class. Number 6, what's the least common multiple of 3 and 7? LCM. Number 6 is LCM. Least common multiple. 21. Yeah, you multiply them. Yeah, now you remember. Very good. Exactly. All right, those number 5 and number 6, special case number 2. You see, I do not surprise you. My test problems are not something like a fancy that you never seen them at all and to surprise you. All the problems are super similar with the examples in the class. And it's in the order that we cover it. When the two numbers are mutually prime, GCF is 1, LCM is their product, right? Remember that? Okay. Number 7, what's the GCF of 18 and 12? Yeah, tell me, 18 and 12. Is that special case number 1 or special case number 2? Do you see a number is a factor of the bigger number, or are they mutually prime? 18 and 12? No, right? So number 7 and number 8, they are the regular case. They are not a special case number 1, not a special case number 2, it's a regular case. In the very beginning, for any two numbers, we introduced a 3-step procedure to find the GCF and the LCM. For number 7 and number 8, you will have to apply the 3-step procedure to find the GCF and the LCM. I will give you a couple minutes first, and you want to look at your notes and then work on this problem. Find the GCF for 18 and 12. What is it? Awesome, perfect. Yeah. Did you apply the 3-step procedure? You just yeah, because this case is not very complicated. Two numbers is not super large or whatever. Yeah, let me apply the 3-step procedure for you. Let's see how do we find the GCF, okay? Step 1, prime factor both. 18 is 18 even number. So we have 2 here, right? We have 9 here. 9 is 3 times 3, correct? So 18 is 2 times 3 times 3. For 12, we know 12 is even. So we have a prime factor 2. Divide 12 by 2, we have 6. We know 6 is even again. We have another 2. Divide 6 by 2, we have 3. So 6 equals 2 times 2 times 3. Right? And then we're going to bubble common factor. That's step 2. Step 3, we multiply them together. 2 times 3, we have 6. That's the procedure. And what if on a test, I give you number 7, number 8, the two numbers are larger numbers? Then it's hard to guess the GCF. Would you like to apply the 3-step procedure to figure it out? You prime factor both, right? And then you bubble the common prime factors. And then you multiply all the common prime factors together. Am I clear on that? Repetition makes perfect. The reason you don't remember because you didn't repeat enough. I mean, it's understandable because you don't use it in real life, right? You don't really have a chance to use those things in real life. That's the reason you have to purposely to practice, to make an effort to memorize, to understand. Number 8, also for 18 and 12, this time we're gonna look for least common multiple. Yeah, how do we find the least common multiple? Yeah, what's the least common multiple? You see, you guess, sometimes you can guess the right, but sometimes you cannot, right? Why don't you apply the 3-step procedure? We also have a 3-step procedure for least common multiple. I give a couple minutes. If you want, you can look at your note. Yeah, you have the note. It's on your note. 3-step procedure for finding LCM. The note that you wrote it on your notebook. Yeah, good job. Did you apply the 3-step procedure? Awesome, thank you. Yeah. Yeah, at least look at your note, yeah, to find the example. How do we apply the 3-step procedure to find the LCM for any two numbers? All right, guys, let me show you. Step 1, prime factor both numbers. Same with earlier, right? Yeah, 18 is 2 times 3 times 3, 12 is 2 times 2 times 3. So we have 18 equals 2 times 3 times 3. 12 equals 2 times 2 times 3. Step 2, I use two different colors. Do you remember that? Yeah. I use red to bubble common prime factors. I use green to bubble the leftover factor. Does that ring a bell? Leftover factors, right? Yeah, in step 3, I multiply all the bubbled factors, but when it comes to common factor, I only run it once, right? One time. So that is this was in the red bubble, this is in the red bubble. And then you multiply by 2 and 3, and this 2 is in the green bubble, this 3 is in the green bubble, right? Yeah, you multiply them all together. What do you have? 36. Yeah, 2 times 3 is 6. 2 times 3 is 6. 6 times 6 is 36. If you time yourself, the whole procedure only take you, did you time me? I was kidding. Maybe just 1 minute, seriously. It won't take you too much time. It will not take you too much time. It's better than you just guess. Sometimes you are lucky you guess the right because those numbers are small, problem easy. Sometimes the problems are harder, numbers are bigger. You might not guess it right. Why don't you just apply the procedure to find it out? Is now a better approach. Yeah, so now let's see the first 8 problems. We have the smallest whole number. What's the smallest whole number? Yeah, what's the smallest prime number? Yeah, so 3 and 4. Find the GCF, LCM, special case number 1. 5 and 6. Find the GCF, LCM, special case number 2. 7 and 8. Find the GCF, LCM, regular case. Okay? Yeah. So this should draw your attention. You should spend time to really grasp those things. Bless you. Number 9. So number 9, we're gonna handle fractions now. We're gonna handle fraction now. Number 9, prime. Okay, number 9 is still like the basic thing. Prime factor 450. I give you 1 minute. Number 9, prime factor 450. Prime factor 450. The big L technique. We start from prime numbers, right? Use the big L technique, 450. Yeah, let me walk around. 450 is a pretty big number, right? I always start from 2 if it's even. And you can right away cut the number in half, right? Well, another trick, if the number, the last digit is 0 or 5, then can you write the factorization? Yeah, what is it? Your notation is different from mine. Yeah, what's the factorization? 450 equals what times what times? Yeah. Good. Yeah. So if the last digit of the number is 5 or 0, it's divisible by 5. 2 to 5 is not divisible by 2. It's not even. Yeah, divide by 5. Let's try that. And make sure all the factors have to be prime numbers. Yeah, 3 is 3. Yeah, 9. Yeah, very close. Very good. Very good. Is 9 prime? If the number is not a prime, you're gonna have to continue, okay? If the number is not a prime, you have to continue. Yeah, this is okay. You don't need a exponent. Can I look at it later? When I finish the class. Yeah. Can I look at your? We do have 1. 1 is not a prime. 1 is not a prime. 2, 3, 3, 5, 5. That'll be okay. 1 is not a prime number. The smallest prime number is 2, right? All right, guys. Let's see. The number is pretty big. 450, right? Remember we talked about this trick. If the last digit of the number is 0 or 5, it definitely divisible by 5, right? So I can start from 5. You might wonder, could I start from 2? Yes, totally fine. But what if I start from 5? Divide 450 by 5, what do you have? Divide 450 by 5, what do you have? Divide 450 by 5. Try your calculator. 90, right? You see that? And 90 is also has the last digit 0. So it means we have another factor 5, right? Divide 90 by 5, what do you have? Divide 90 by 5. 18. Is 18 even? 2. 9 is 3 times 3. Okay? So if you want to start from 2, totally okay. I always start from 2 because 450 is even. Divide 450 by 2, we have 2 to 5, right? And 2 to 5 is not divisible by 2 anymore. It's not even, but it's divisible by 5, right? Divided by 5, what do we have? 45, right? And the 45 is 5 times 9, 9 is 3 times 3. So the order doesn't matter, but you need to make sure every step is correct. All the factors are prime factors. All right? Very basic. That's the first technique we have learned. So when you look at the answer choices, the one you should choose is 450 equals 5 times 5 times 2 times 3 times 3. The order of the factors doesn't matter. And that's the thing you're gonna look for. Okay, 1 will not be in the prime factorization because 1 is not a prime number, right? Am I clear? This might be the last chance we learn those topics because later we're gonna move on new topics. Number 10, reduce fraction. The fraction is 10 over 12. Let's reduce fraction 10 over 12. I'll give you a few seconds. This one is so easy. How do we reduce this fraction? Divide by, okay, we can divide by 2. Yeah, exactly. Because 10 and 12 are both even, right? We divide by 2, divide by 2. What do we have? Do we have a 5 over 6? Yeah. Is a 5 over 6 prime? Is a 5, 6 reduced? Yes, because 5 and 6 are mutually prime. We talked about this before. If the numerator and the denominator